Okay, now we solved for Ka in the last one, but most of the time we know Ka. And we have hypochlorous acid. We can look in a table, and this is HClO. And the Ka for it is 3.5 times 10 to the minus 8. The table in your book gives it 3.5, no 0, but I want to always have three significant figures, so we'll just go with that. So if you know Ka, then the thing that is going to be unknown are the concentrations. The concentration of the acid at equilibrium, H3O plus, and A minus at equilibrium. So call this HA. We could certainly call it HClO because that's such a small acid, it's not that hard. That's the only reason we write HA is because it's quicker. I'm just going to write HA so we just don't get out of the habit of doing that. That is entirely up to you. And then we have ICE. And then we have 0.350 molar, 0, 0, minus X, plus X, plus X. 0.350 minus X, X, and X. Now, these are our equilibrium values. We don't know what X is yet, so we don't have the numerical values yet, but we can plug it into our Ka expression. Now here I've left over, before I'd write out Ka and I'd write the concentration of H3O plus times the concentration of A minus over concentration of HA, and then fill in the blanks. I'm just jumping right here. If this throws you off, then go back to the earlier lectures until you see how I got here. Or write it out yourself. Write out the Ka expression, and then fill in with these values, and you should get here. Now, we can solve for X here. That's just using the quadratic formula. But to save ourselves some time, we can use an approximation that will get rid of this X. And the approximation, if it holds, it means that X is such a small number that if we subtract it from this number, we'll just round back to that number anyway. We'll end up with something like 3.4999998 or something like that, where we'd have to round back here anyway, so we can get rid of it. But we have to make sure that we're allowed to do that. If X turned out to be 0.25, we certainly couldn't get rid of it. We'd be way, way off if we ignored X. So we don't know what X is yet, but we are guaranteed that if the concentration of the acid over the Ka is greater than 100, we'll have less than 5% error. And the larger the number is, the higher it is above 100, the lower the error. So if we get a number that's in the thousands or millions, then we can be guaranteed that we will have way less than even a 1% error. So anyway, the thing is that we know if this works, then if this is true, then the approximation holds. So that's what we're we're hoping for here. So the concentration of the acid is 0.350. The Ka happens to have the same numbers, but that's just by chance. And this turns out to be 1 times 10 to the 7th. 10 million. That's certainly larger than 100. And it's so much greater than 100, we can assume that X is going to be a very small number. And we'll see that when we do out our calculation. So what that means is since the approximation holds, definitely holds, we can rewrite this as X over 0.35 is equal to 3.5 times 10 to the minus 8. What we've done is we've just gotten rid of that X. Now it's pretty easy because we just multiply these numbers together, take the square root, so X is then going to be equal to 1.11 times 10 to the minus 4 molar. And I'm not working through all of that algebra. You should be able to do that. And if not, go back to the earlier problems where we worked everything out step by step by step. Now we have this X, so this is the concentration of H3O plus, and it's also the concentration of A minus. They wanted all the equilibrium concentrations, so HA at equilibrium is going to be 0.35 minus X, so that's going to be, what's it come out to be? Oh, yeah, and X, since it's so small, this comes out to be 0.349889. I'm just writing it out so you can see, and then that's going to be, it's going to round back to 0.350 mole. So X was so small that even though some of the acid had to dissociate to create the H3O plus and A minus, it was so small that it's not noticeable. It rounds away. And so, well, how can that be? How can these be the same after? Well, so we have to go with the precision of our calculation. If X is that small, then we can say it was approximately unaffected, even though there was a slight bit of it used up. So we have our concentrations, and then our pH. pH is just the negative log of the concentration of H3O plus. So the negative log of 1.11 times 10 to the minus 4. And then this comes up to be 3.95. So that's our last thing that we have to do. Now we're going to be using the quadratic formula for some of where the approximation doesn't hold. So for some of the problems we do later, you're free to go back and use the quadratic formula to solve this with the x in there, and you should find that actually I did it on my computer. It'll take too long to write out. But if you do it this way or by this way, they round to the same number. That's unusual. It's because this Ka is so small. But what you should normally find is that the difference between them is very, very slight. Okay, let's do, make sure everything's on there. We have 2 here. Okay. Go a little bit faster. This is nitrous acid. The Ka for this is found in a table in our book, and it's 4.50 times 10 to the minus 4. Ha, oops, that's H2O. Now, on my exams, I'd want you to write this out. You might see that, well, I can just put everything directly into the Ka expression. The problem is when people make mistakes on my exams, I have nothing to work with then. You got the wrong answer. And basically, you plug all this stuff in, you skip all of this, and then we go right here, and we get x squared. And for some of my students that this is almost incidental too, this kind of scribbled out and then they put in the x. You want to put the full workup on my exams, if you're taking my course, so that I have something to work with in case you make a mistake. There you can see there's lots of things that can go wrong here. Now this is the, we're checking for the approximation, see if we can get rid of that x. This turns out to be 3,444. It's certainly greater than 100, so the approximation does hold. Again, that will be beneficial because we can just get rid of this. And if you're uncomfortable with getting rid of that x, try it for yourself. Do it out this way and then do it out with the x in there with the quadratic formula. You should find that the answers are extremely close, and sometimes they'll round to the exact same answer. This is still very large. It's not as large as the 10 million we had last time, but we should still expect that the error to be extremely small. Okay, so we have the x is the concentration. Oh, actually no, x is what we're finding here. And x is 0.0264 molar. And so that's the concentration of H3O plus, which is also the concentration of A minus, and the concentration of HA is going to be 1.5 molar minus x, or minus this number. And you can see here we end up with 1.52 molar. So this was a smaller K, which means the approximation, though it didn't hold in a huge way. This is just 3,000 versus 100 rather than 10 million versus 100. So x is larger, and it has more of an effect, a final effect on the equilibrium concentration of the acid. It didn't round back to 1.55. We actually took away a significant amount. So now we have all the concentrations. We have the pH. Oh no, we don't have the pH. The pH is going to be the negative log of the concentration, and so this is 1.58. Because there was more of the acid, even though we started with different concentrations, they weren't that much different. We had a higher concentration of H3O plus. We should expect the pH to be lower. So actually, so that we can tell that the pH should be lower just from here, but we should also expect the degree of ionization to be larger for nitrous acid, though we're not asked to find that here, so we're not going to do that.